Monocular 3D object detection with bounding box denoising in 3D by perceiver. Although significant progress has been achieved in monocular 3D object detection, accurate 3D center localization remains a major challenge for state-of-the-art methods. Most of these methods follow a bottom-up paradigm, where a single 2D image is used to directly predict 3D bounding boxes. However, due to the inherent depth ambiguity of this task, relying solely on bottom-up 2D to 3D paradigms may not be enough to completely address this challenge. Our method has motivated a strong empirical upper bound experiment. We analyze vehicle detection performance on KITTI validation set. We use the recently proposed Monocon because it achieves SOTA performance with a very simple design. By using Monocon's prediction results as bottom-up 3D anchors, we sample 3D bounding box proposals along both the X and Z axes with a simple strategy. We use all the generated 3D bounding boxes as top-down proposals and compute the empirical upper bound of 3D detection performance by searching for the best match within top-down proposals for each ground truth 3D object bounding box based on 3D intersection over union. The experiment shows that, despite the evaluation result of initial bottom-up proposals is relatively low in 3D average precision, most of predicted 3D centers are already in the close proximity of the GT ones. An empirical upper bound of 34.4 AP3D can be achieved even with a coarse sampling scheme, which is significantly higher than SOTA methods. We also obtain similar observations from other backbone 3D object detectors. These strong empirical observations demonstrate the potential of integrating the bottom-up initial proposals with top-down sampling and verification. However, this improvement also comes at a cost. The 3D to 2D proposal verification phase can be treated as a 3D bounding box denoising process, as we want to search for the best bounding boxes from the top-down proposal set. This process is extremely challenging, as the proposals generated from the same bottom-up anchor are highly overlapped in both 3D and 2D after projection. In our work, we propose to fuse these 3D to 2D geometric feature with their correspondent appearance features to learn discriminative features for bounding box denoising. We present a method of using the perceiver I/O model to effectively fuse these contexts. Our monocular is divided into two stages, bottom-up proposal generation stage and top-down denoising stage. We generate bottom-up proposals using one off-the-shelf backbone monocular 3D object detector which is first trained following its own training receipts. For the top-down sampling with a bottom-up anchor proposal, we start by generating a 2D local grid in the XZ plane, centered at the position, X, Z, of the anchor box B. We adopt a conservative strategy using the search range plus or minus 1.5 meters and the stride 0.75, which will generate 25 proposals per bottom-up anchor. We then place the anchor box B at the 25 grid points, with only the position P updated. In the 3D to 2D proposal verification stage, we utilize three types of features in encoding a 3D bounding box proposal, including the geometric encoding, projection point appearance encoding and 2D ROI appearance encoding. For geometric encoding, it takes the normalized 3D box parameter and normalized 2D projection point coordinates as input, use a MLP to encode the feature. For the projection point appearance encoding, we directly extract features from the final layer of the feature backbone. We further encode the feature using another MLP. For the ROI appearance encoding, we use the ROI align features extracted from the final layer of the feature backbone. We use a third MLP to encode its appearance feature. With the above proposal embedding, our goal is to compute a final latent feature representation in the D-dim space for each proposal by fusing information from the geometric encoding, projection point-based appearance encoding and ROI-based appearance encoding, such that we can address our unique challenges in the proposal space. We leverage the perceiver I/O model for this intra-proposal attention. We first treat projection point appearance encoding as query, and computing key and value from the geometric encoding, followed by a self-attention module. Next, the perceiver fuses the ROI appearance encoding as the 1-token query with the 9-token geometry-aware projection point encoding using a cross-attention module, which results in the D-dim latent features for each proposal, which fuse the three types of information sources, geometry, point-level appearance and region-level appearance. With the compact latent vector computed for each proposal. To that end, we treat each proposal as a token, and apply a standard self-attention module to capture the inter-proposal attention. This verification is posed as a regression problem, where L is the total number of categories and Y is the classification scores, logits. Delta N and delta N are the position and dimension residuals. Our monocular is trained with a fixed set of 3D bounding box proposals and a fixed set of ground truth 3D bounding boxes. The ground truth assignment for proposals is needed in training. Due to the crowding issue in the proposal space, we observe that both of them do not work during our development of the monocular since they will create difficult decision boundaries for the monocular to learn or fit. Since we have the two fixed set as input, therefore, we resort to the set prediction formulation used in the Dieter framework. We use the classification loss, normalized L1 2D bounding box, 2D IOU loss and 3D IOU loss as our final cost function. We evaluate our monocular on the well-established KITTI dataset and the large-scale Waymo dataset. Our improved baseline detector outperforms previous SOTA methods on the KITTI benchmark by a large margin. In order to demonstrate the ability of the proposed monocular to generalize across different detectors, we utilize three distinct base detectors with varying levels of detection accuracy. We observe that monocular consistently yields significant improvements across all three base detectors. In order to showcase the generalization capabilities of the proposed monocular on large-scale datasets, we conducted testing on the challenging Waymo validation set, utilizing two SOTA methods. We observed consistent improvements in performance. Although our monocular causes about an average of 8 milliseconds overhead compared with baseline detectors, it still achieves real-time detection. We provide ablation studies of monocular structure in different bounding box branches. It shows that perceiver effectively fuses information between appearance and geometric embeddings. It also shows that the rescoring head branch plays a crucial role in filtering out false detections, leading to significant improvements by up to 3.3 AP. The localization residual branch and the dimension residual branch further enhance the performance by about 1 AP. We provide qualitative comparison with baseline methods on KITTI dataset. Thank you for watching. Please check our page for more detailed information.